Hey math fans, Alex here, and in the last video we used the binomial distribution and realized that with a large enough number of Bernoulli trials n and a small enough probability of success p, we can actually approximate the binomial distribution with something called the Poisson distribution. Okay, so just to give you an idea, the Poisson distribution has a random variable x which only relies on one parameter lambda, and what I didn't mention before is that you can think of lambda as the average number of successes in some interval, usually a continuous interval like time. Okay, but it could also be in some sort of like area is also continuous, and you can count like the average number of bacteria in like a continuous circular region. Okay, so then what we discovered is that the probability distribution of Poisson is the probability that x takes on k successes is just going to be this lambda to the k over k factorial times e to the minus lambda. And now what we're going to do is we're going to discuss the two main properties, expected value and variance. So it turns out that both of them are the same and they're just lambda. So let's see why that is. Okay, so proof. And one important aspect of this proof is going to recall that the exponential function, e to the x, is just going to be the infinite sum from k equals 0 to infinity of x to the k over k factorial. Okay, so that's going to be pretty important. Okay, so to prove 1, we have to find the expected value that the number of successes is, we'll say, k. And to do that, recall that that's just going to be the infinite sum from k equals 0 to infinity. Technically, it's minus infinity to positive infinity, but remember the Poisson distribution is only really defined in this interval. And then we take that times k times the probability that x is equal to k. Okay, but Poisson distribution, remember this quantity here is going to be equal to what? It's going to be lambda to the k over k factorial times e to the minus lambda. Okay? Okay, so this quantity over here was the Poisson distribution. And now what can we do from here? Well, we can cancel out one of these k's with one of the k's in this factorial. Okay, remember that, if you don't remember, k factorial was just k times k minus 1 times ... all the way until you're multiplying 1. Okay, so another way that you could write this is you can write k factorial as k times, and then everything below k multiplied together, which is simply k minus 1 factorial. Okay, so that's exactly what we're going to do. So one of these k's is going to cancel, and we're going to be left with that this is going to equal, well, the first thing that I'm going to do is actually pull out the e to the minus lambda. That has nothing to do with k, so we can just pull it outside of the sum. So this is e to the minus lambda times the sum from k equals 0 to infinity of, now this k is going to cancel with one of these, and we're going to be left with lambda to the k all divided by k minus 1 factorial. Okay, now, this quantity right here, this quantity is almost e to the lambda. If you look at the definition right here, remember e to the lambda would be lambda to the k over k factorial. We almost have that, okay? In order to make it exact, what we're going to do is we're actually going to do an old trick, which is going to be to multiply and divide by a lambda. Okay, so what we're going to actually do is we're going to kind of multiply this by lambda to the minus 1 power times lambda. And you'll notice that this is just 1, and I'm multiplying by a very special 1. And what is that going to get me? Well, I'm going to pull this lone lambda outside now, and this is going to equal lambda e to the minus lambda times the sum from k equals 0 to infinity of lambda to the k times lambda to the minus 1. That's going to be lambda to the k minus 1 over k minus 1 factorial. And really, I should change the bound on the sum, because it no longer works for k equals 0. But now this, by definition, is still e to the minus lambda. Or I'm sorry, it's e to the lambda, right? So this infinite sum is really the definition of e to the power of whatever this number is. Okay, so I get that this is lambda e to the minus lambda times e to the lambda. But then the e to the lambdas cancel, and I'm just left with lambda. Okay? Now, I'm not going to prove 2. You're going to do that as an exercise, but I will give you a hint. But consider, instead of trying to find the expected value of x squared, because remember, variance is the expected value of x squared minus the expected value of x quantities squared. Instead of doing that, don't do that. And instead, you're going to find it very helpful to instead consider the expected value of x times x minus 1. Reason being, the proof is going to be very similar to this, where this time you're going to actually cancel out, if I go back up here, you're going to cancel out a k and a k minus 1 from the k factorial, and you're going to take it from there. All right? Okay, so now let's go ahead and consider some examples of the binomial and the Poisson distribution. Okay, so example 2 is the lottery ticket problem. We all have lottery tickets. States have their own specific ones. Of course, there's Powerball, Mega Millions. And the question I want to ask is, how many lottery tickets do I have to buy in order to make the probability of winning at least capital P, where capital P is just a percentage, anywhere from greater than 0% to probably less than 100%. You can't guarantee winning unless you literally buy every single lottery ticket. So that's kind of infeasible. So you can at least reduce it to a probability. So the idea is we're going to go ahead and let capital N be the number of total lottery tickets out there. Capital W is going to be the number of winning tickets, whatever that means. Okay, maybe it's the winning ticket is like the Powerball ticket, or it could be getting a prize over $100. Okay, well then the probability of a success, getting a winning ticket, little p, is just the ratio of the winning tickets to the total number. And then the trial is just drawing a lottery ticket, buying a lottery ticket. And the question that I want to ask, are these Bernoulli trials? Are they independently and identically distributed? Well, yes and no. In a technical stance, no. Buying one ticket reduces, let's say you buy a dud, that's going to increase the likelihood that the next ticket bought will be a winner. But the increase is so negligible that we can just assume that all these trials are independent. And that's kind of the difference between theoretical and experimental, right? So theoretically, it's nice to be independent, but in the real world, it's almost impossible to be exactly independent. But we can make that assumption. Okay, and we're going to let little n be the total number of trials, and let's see where we go with this. So since we're trying to wonder what distribution to use, do we use binomial or Poisson? Well, since little p is clearly very small, I mean, I guess it depends on what prize that you want. If you just want like any cash prize from $1 up, then maybe little p is a little bigger. But if you wanted like hundreds, if not thousands of dollars, probability of that winning ticket's very small because there are less in the pool. Okay, and the required number of trials is very big as well. You're not expected to draw 5 tickets and then automatically get a winner. You're going to have to draw hundreds, if not thousands. Okay, especially if you want the probability of success of winning to be big as well. Okay, so 30% likelihood, okay, maybe not so big, but if you want a winning ticket with percentage 90%, then yeah, it's not going to happen without a large number of trials. Okay. Then we can say that the probability of having a winning ticket is approximately what? What kind of distribution would that be? Well, it'll be approximately Poisson, right? Because number of trials is big, probability of success is small. So it's approximately Poisson with parameter lambda equal to what? Well, maybe I'll do this in a different color. Remember that, we approximated lambda as little n times p, where n was the number of trials, and in this case, the probability of success is this quantity right here. So capital W over capital N. That's our parameter. Okay, so now we can just kind of do the math. So now here's the actual math portion. This was all kind of set up. So if the random variable x represents the number of successes and of course n trials, n Bernoulli trials, what do we want? We want at least one winning ticket. And we need that to occur with probability capital P. Okay, so we need probability of x being greater than or equal to 1 success. We need that to equal capital P. Okay, but we can plug in on the left side. So this is going to imply what? Well, first things first, this is ordinarily very difficult to calculate because getting at least 1 success means I can have 1 success, 2 successes, 3 successes, all the way up until n trials where n is obscenely big. But a trick that you're commonly going to use is just take the complement instead. So this is going to be 1 minus the probability. What's the opposite of getting at least 1 success? Well, that's going to be the probability of getting strictly less than 1 success. The only time you can get less than 1 success is to get exactly 0 successes. And that's going to equal capital P. Okay, but we can rearrange this, right? And we get that the probability that x is equal to 0 is going to be 1 minus this preset probability. Okay, so the Poisson distribution says what? Well, the probability that x is equal to 0 is going to be lambda to the 0 over 0 factorial times e to the minus lambda, right? That's the definition of Poisson when x is equal to 0. That needs to be 1 minus p. Okay, so this is right here. This is Poisson, where x is equal to 0. Okay, and then we can finally go ahead and kind of substitute in for lambda. Okay, so first of all, this is 1, that's 1. So what we're going to get is that e to the minus lambda, which recall was little n times this ratio, that needs to equal 1 minus p. Okay, so odds are you're not going to get exactly equal to 1 minus p, right? Because all of these are going to be whole numbers, so you really have no control on whether the exponential function is going to get you exactly a probability. But just be as close as you want. So I'm going to say maybe approximately equal to that. And yeah, that's essentially the answer. So we want little n that kind of gets this as close as possible. Right, so I'll just go ahead and note that, and then I'll give you a practical example of this. So we want big enough n to get as close to 1 minus p as possible. Okay, so usually, you can use natural logs and solve for what the exact value of n is and then just round. In fact, let's do that right now. So some states actually release the data for their lottery tickets, like New Jersey. So let's consider some more practical example. So consider the power play in New Jersey. Then I'm going to hit you with some numbers. And let's say, because they don't just have one grand prize, they have a lot of smaller prizes. Let's say I want $100. I want at least $100. Okay, so let's say that you want, say at least $100 with probability big P equals 90%. Okay. So how many tickets do you need to buy? Okay, and then this is pretty straightforward, right? So I'm just pretty much gonna copy this down. Okay, so should probably give you the data as well. So the information is that the number of winning tickets, I went ahead and just counted all the ones, or added up all the ones that were at least $100, and there were 12,493, which might sound like a lot, but how many total number of lottery tickets were there in New Jersey? 4.8 million. Okay, so the probability little p of success, which was this ratio, when you go ahead and plug that in, you're going to get around 0.0026. So now you see what I mean by this is a good approximation. This is a good candidate for the Poisson distribution. Okay, there are going to be a lot of trials because the probability of success is so small. So we need that e to the minus and then this quantity times n. Well, okay, maybe I should show a little bit more work. So we need e to the w over capital N times n. We need that to be as close to 1 minus probability of success as possible. Okay, so plugging in the numbers, we know that this ratio is the 0.0026, so we get e to the minus 0.0026n. We want that to be as close to 0.1 as possible. How are we going to solve an equation like this? Do my favorite thing and hit it with a log on both sides. Just take a natural log. Okay, and then what do we get? And we get that minus 0.0026n needs to be approximately the natural log of 0.1, and then just divide both sides by this negative 0.0026. Okay, so number of tickets that we need to buy is the natural log of 0.1 divided by minus 0.0026, which gives us approximately, if you round, about 886 tickets. And just if you were curious, each of these tickets is worth $5, by the way. So this is times $5 a ticket. this is fun math. So how much would you have to spend in order to guarantee with only 90% accuracy that you're going to win at least $100? Well, my friends, that is $4,428. I'm going to put a big frowny face and say, don't bet on the lottery, kids. Let's move on to our next example. All right, example 3 says, it has been found that 80% of all printers used on home computers operate correctly at the time of installation. It's not true. This is just for the sake of the problem. The rest requires some adjustment. A particular deal sells 10 units during a given month. Part A, find the probability that at least 8 of the printers operate correctly upon installation. Okay, so the first thing to note is that each printer being sold is a trial in some sense, with either success or failure. The success in this case is operating correctly, or in other words, just working, or a failure, which is not working. Okay? Each trial is what? Well, each trial is independent of each other, relatively speaking. I mean, if you look at a printer and it works or it doesn't work, that's not going to influence whether or not the next printer works or doesn't work. Okay, so we can say that each trial is independent. Is it identically distributed? Well, we're given that the percentage of success is just 80%. Okay, so that's going to hold whether you look at 10 units or 100 units. So each trial is going to be independent and identically distributed, meaning it has the same probability to occur. Okay, so your initial guess is the binomial distribution, but given the previous example, you might be inclined to think that we can approximate that using a Poisson variable. Okay, well remember, in order to use a Poisson variable, we need 2 things. Okay, so can we use Poisson? Okay, so remember, in order to use Poisson, the first question that you need to ask yourselves is, do we have a big sample size? Do we have a large number of trials being conducted? Well, the dealer is selling 10 of the units in a month. That is not a lot of sample size, so we're gonna say no on that. Definitely not. And what was the other condition? Well, the other condition was that you had a very small probability of success. Okay, so do we have a small little p? And the answer is also no. 80% is not small at all. So the answer is no. We cannot use the Poisson distribution, which means we have to use binomial. Okay, so what are we trying to find? We want the probability that at least 8 of the printers operate correctly. Okay, so we're going to go ahead and let x be the random variable of number of printers that are operating correctly. Operating correctly. Then we have that x is binomial. So x is binomial with sample size 10 and probability of success 0.8. So we want the probability that at least 8 of the printers operate correctly. So we want the probability that x is bigger than or equal to 8. Okay, so what's that going to be? Well, I don't know. What you could do is plug it into the calculator, which is a totally fine thing to do. I'm going to work this one out by hand, But what this is it's going to be the probability that x is equal to 8 plus the probability that x is equal to 9 plus the probability that x is equal to 10. Okay, since it's discrete and honestly adding 3 of these probabilities up is not that much, we can just do it by hand. Okay, so what's the probability that x equals 8, for example? Okay, well, I'm just going to do perhaps one of these. Okay, so the probability that x is equal to 8 is going to be n choose 8 times the probability of success raised to the 8 times the probability of failure, which has to be 0.2, and that's raised to the 10 minus 8, which is also 2. Okay, so that's what it would be. Plus, I guess we can do the other ones as well. So probability that x is equal to 9, that's going to be 10 choose 9 times 0.8 to the 9 times 0.2 to the 10 minus 9. So that's 1. Plus 10 choose 10, 0.8 to the 10, and 0.2 to the 10 minus 0, which is, or I'm sorry, 10 minus 10, which is 0. Okay, so the 0.2 doesn't really need to be written there. Okay, but when you plug in the numbers, you're going to get that this is going to be equal to 0.6778. Now, just as an exercise, and I didn't actually do this in my notes, but what would you get using Poisson? So remember I said we couldn't use it because that would be a very bad approximation. Well, let's test that out. So go ahead and just compute what that is using the Poisson distribution, and you should get something radically different from 0.6778. Okay, so that's it for part A. You'll notice part B was kind of written for part A because it says, find the probability that at least 8 of the printers operate correctly, which we've done, but this time for 6 consecutive months. Okay, so we found out what it was for 1 month. Now we're trying to find it for 6 consecutive months. Okay, so this isn't actually that bad. So remember that maybe we'll let perhaps A1 be the event that 8 printers, or I should say at least 8 printers, operate successfully in month 1. Okay, and then really, A2, A3, etc. I'm not going to really define the rest of these, but you can kind of see where I'm going with this. And in order to satisfy that, the probability, we want the probability that A1 occurs and A2 occurs and all the way until A6 occurs. So that's what we're trying to find. Well, the probability that at least 8 printers operate successfully in any given month is going to be independent month to month. Okay, because the probability is just going to be 80%, just overall. Okay, that's kind of a universal probability for this question. So if he sells 10 units in a given month, we can go ahead and assume that those are all independent. And remember that with independent events, if you're taking the probability of an intersection, that's going to essentially be the product of the probabilities. So this is going to be probability of A1 times probability of A2 times ... times the probability of A6. But wait a minute, I just said that they're independently distributed, which is why we're allowed to multiply, but they're identically distributed, which means that that probability is the same as that probability. They're all going to equal whatever the answer was from part A. Okay, so really, this is all going to be the same as the probability that the random variable x exceeds 8, and we're raising that, because we're multiplying it by itself 6 times, so we're raising it to the 6th power. Okay, so we're just going to go ahead and take whatever we got, so 0.6778, and just raise it to the 6th power, and we get 0.0970. So notice that that little thing happening 6 months in a row has a lot smaller of a chance happening than just happening for 1 month. Okay, so that's example 3. All right, so the last example that we're going to talk about is radioactive decay. So there are processes in nature where nuclei just kind of randomly turn into other nuclei and release a kind of energy, okay, which is radioactive decay. And radium is an example of an element that does that. Okay, certain kinds of radium decay into radon by emitting what are called alpha particles. You don't really need to know what an alpha particle is. It's kind of a helium nucleus. But what you do need to know is that for every alpha particle created, that clues you in to one radon or one radium being converted to a radon. Okay, so the events of the radium nuclei being converted to radon nuclei, those are roughly independent. So if one occurs over here, that's not going to influence the probability that others occur. It's completely random. And what we do know about radioactive decay is we have a measure called the half-life. That is the time that it takes for half of all of a given sample to decay. Okay, so in this case, this process takes 1,600 years for the initial amount to decrease by a factor of 2. Okay, so a couple of things. I went ahead and kind of summarized the periodic table entry for radium. And remember that, this 88 here is the number of protons, which we don't really care about. But for the purpose of this example, this 226 represents the number of grams. The number of grams in approximately this many particles, 10 to the 23rd power particles. That's a lot of particles. We want to try to figure out what distribution we can use to model radioactive decay. And this gives you a pretty good indication. Okay, but let's just kind of go with it for a second. So with all of this information, what we can say is that there are 10 to the 23 particles. 10 to the 23 particles in 226 grams of radium. So let's suppose that we actually start with a single gram of radium. Okay, well, how many particles would there be in just a single gram? Well, this would be divided by roughly 100. Okay, so that's going to imply that we have approximately, 10 to the 21 particles in just a single gram of radium. Okay, and when I say particles, I mean atoms of radium. Okay, so with this information, what we're going to go ahead and do is we're just going to go ahead and set the initial amount. We're just going to assume that it's 1 gram, or in this case, 10 to the 21 particles. Okay, so you can kind of think of that as our sample size. So we only have 1 gram of the stuff. Out of 10 to the 21 particles, we're trying to figure out which ones are going to decay, which ones aren't, and the probability of all that occurring. And what we can say is we want to go ahead and define a success. Define a success as a radium nucleus decaying to a radon nucleus in 1 second. Okay, so why am I bringing up time? Well, we know that half of them are going to decay in 1,600 years. Okay, so we should be able to kind of pinpoint kind of what that is. Okay, so we probably need to figure out, kind of on average, how many radium nuclei decay in a single second. But we know that if it takes 1,600 years for half of it to decay, think about what that means from this equation. If half of this decays to this, and every time one of these decays, an alpha particle is released, that means that you're going to have n0 times a half numbers of alpha particles. Okay, so if it takes 1,600 years for, we can say, the number of alpha particles to be half of n0. Well, what's half of n0? Well, if n0 is 10 to the 21, this is actually 10 to the 21 times, say, like 2 or a factor of 3 or something like that. So realistically, if we cut that in half, order of magnitude says that we're still going to get about 10 to the 21. Okay. And we want to know how many alpha particles are generated per second. Okay, so how many would be generated per second? Well, let's think about it for a second. So if we have 10 to the 21 particles, I should probably specify alpha particles, being created over 1,600 years, we can kind of do a little of what's called stoichiometry. So let's see, 1 year, 365 days. 1 day has 24 hours. And in 1 hour, there's 3,600 seconds. Okay, so then what we can do is these are the same. 1 year is equal to 365 days. So we're just multiplying by a bunch of ones is what we're doing. But notice that the years cancel, the days cancel, the hours cancel, and we just have the number of alpha particles created per second once we do this computation. Okay, so when you kind of do the math, you'll discover that that is going to be on an order of magnitude of about 10 to the 10 alpha particles that are produced per second. Okay. So again, if we define a success as just one of those being generated, one of those alpha particles being generated, and it turns out that, 10 to the 10 are being generated per second, then what we can do is we can find the probability of success. Okay, we can find that fairly easily. So the probability of success is then going to be equal to the total number of alpha particles that decay a second, which is about 10 to the 10. And we're dividing that by the total number of particles, which, remember, we started with 10 to the 21 power. Okay, and that means that on average, you get a probability of success of 10 to the minus 11. Think about it for a second. If half of the particles are expected to decay in 1,600 years, what are the odds that one of them is going to decay in just 1 second? Very small. Okay, and in fact, this should also clue you into what distribution we're going to be using, because this is very small. Okay, and just to remind you, we had that the initial number of particles, we had that n0, in a single gram of the stuff, we got 10 to the 21 power, which is a very big number, I would say. Okay, so we have a very, very small probability of success, if success is defined as a decay of a single nucleus in a second. And we have a very big sample size, so if your guess is that we're going to use the Poisson distribution, you'd be correct. And in fact, let's go ahead and describe it like that. So let x1 be the number of decays of radium to radon in 1 second. Well, then by everything we just showed, we know that x1 has a Poisson distribution with parameter we'll call lambda, where lambda is equal to total number in our sample, total number of trials essentially, times the probability of success. Okay, but it might be a little bit more useful to try to think about this in terms of a different random variable. Okay, so let's consider the random variable xt, where xt is the number of decays that occur in t seconds. Okay, it's not at all obvious what this distribution is at all. Okay, but what I can tell you is that xt can be thought of as taking the distribution x1 and just adding it to itself, t times. Okay, so the question is, that I'll leave you with, what's the distribution of xt? Because remember, when you start adding 2 or more random variables together and you want to find the PDF, you have to do a convolution, which involves a messy integral. Okay, so it's a reasonable question to not know right off the bat what this distribution is. Well, I'm actually going to tell you the answer, and I think this is going to constitute an exercise. The answer is that xt is actually Poisson. Okay, now it's not going to be the same parameter lambda, clearly, so maybe I'll define it as, maybe lambda t, where lambda t is going to be t times n0p. Okay, but yeah, it is true that even 2 kind of different Poisson distributions, when you add them together, you still get a Poisson random variable. But nonetheless, we can describe radioactive decay with the Poisson distribution, and there you go. So hopefully that was helpful, and I will see you in the next video where we talk about continuous distributions. Have a great rest of your day.